Hello, everyone. I've given this talk a couple of times before, but it was never recorded, and some people wanted to see it. So here is an unofficial recording of this talk. So when measurable spaces don't have enough points. This talk is based on joint work that I've done this year with Sean Moss, 2022, and on earlier work that I've done with Tobias Fritz and Charvin Razakoli. The idea is that working on categorical probability, we came across a situation where measurable spaces seem not to have enough points sometimes, in the same way as sometimes topological spaces do. And so this can be thought of as one possible entry point to point-free measure theory, a little bit like people do point-free topology. So let's see. First, let's recall measurable spaces. You might be familiar with topological spaces. So a topological space has a topology in the same way a measurable space has a sigma algebra, which is a subset of a power set, so a set of subsets, which contains the whole thing in the empty set. Now, in topology, you want to have finite intersection and arbitrary unions. With sigma algebras, there's not that much difference between unions and intersection because you want complements, all right? So this duality between closed sets and open sets breaks down here because we have complements, so they are kind of on the equal footing. However, you only want to have countable unions, all right? So if in topology you take arbitrary unions and finite intersections, here you want countable unions. And as we'll see, sometimes the role of finiteness in topology is played by countability in measure theory. Now, just as well, just like for topology, recall that a function is continuous if three images of opens or of closed are open or closed. And for measurable spaces, we have the same. Pre-images of measurable sets are measurable, okay? So these categories of like topological spaces and of measurable spaces are very similar. They're both bifiber over set, meaning that these are just sets with an extra structure, and you can pull back and push forward these things. Like you can have these induced and co-induced topology, sometimes called initial and final, and the very same thing can be done for sigma algebras. Okay, so you can induce and co-induce sigma algebras in the same way. The similarities between these two categories do not stop here. So we're going to see now that the similarity between these two concepts goes much deeper than we thought. All right, so first of all, sometimes in a topological space, when the topology is not very fine, like it's coarse-grained, it fails to tell points apart. Like the technical term is, it fails to separate points. Look at this drawing you see, like here, the topology can tell, for example, Z apart from X, but it cannot tell apart X from Y, all right? So this situation, which is for every A in the topology, for every A open, X is an A if and only if Y is. This situation here is an equivalence relation, and this implies that X is equal to Y when the topology separates points. So whenever this happens, and it's the same point. But you see in this picture, this fails to happen. Now, we can just say the same for sigma algebra, exactly in the same way. The only minor difference is that since sigma algebras have complements, so here you see in this picture, Z is somehow more specialized than X and Y. This is not the case for sigma algebras, because in sigma algebras, you can also take the complement of this blue set, all right? But for the rest, they're the same. So you can just transpose this notion. And sometimes sigma algebras can't tell points apart from one another. All right. There's an equivalent condition in topology, which is the topology separates points if taking the closure of a point is an injective operation. So if the closure of X is the closure of Y, then X is equal to Y. All right. So for example, if the closure of X is equal to X, this holds. So for all T1 spaces, where all points are closed, this holds, but not more in general. So you see in this picture down here, the topology separates X and Y. And if you look at what's the closure of X, that's the largest, sorry, that's the smallest closed set containing X. Now, closed sets are complements of open, so the smallest closed set containing X is this set. And you see this set does not contain Y. So it cannot possibly be the closure of Y. All right? So this is an equivalent condition to saying that the topology separate points. All right. Do we have something like that for sigma algebras? It's a bit more complicated, right? Because now there's complements, so there's no closed sets. I want to argue that sometimes measures do that. All right. So here's an equivalent condition. Taking the Dirac delta measure over a point is an injective operation. Now, what's the Dirac delta? So you can imagine the Dirac delta as being a measure that gives mass 1 to the point and 0 to everything else. More rigorously, it gives measure 1 to all sets that contain X and 0 to sets that don't contain X. All right, that's a well-defined measure. It's even a probability measure. And now, if the delta over X is equal to the delta over Y, then X equals Y, if and only if your sigma algebra separate points. So taking the closure of a point in topology is a little bit like taking the Dirac delta over a point in measure theory. Okay? It's a kind of injectivity condition here. That's the first of these maybe not so well-known analogies between topologies and measure theory. And again, we will not stop here. There's a lot more to be said. So there's not just a condition of injectivity, but a condition of, so to say, exhaustion. Let's make this more precise. So in topology, you know that when you can take a union of two closed subsets and their union is again closed. Same thing for finitely many. And you can view this as a way of forming larger closed sets from smaller ones. All right. So you can consider closed sets as kind of building blocks to construct more complicated ones. Now, you call an irreducible set a set that cannot be obtained in this way, non-trivially. So basically, if you write it as a union of two closed sets, well, then one of them was the closed set already that you wanted to do. Okay? So this is an irreducible closed set. Now, every closure of a point is irreducible. You can check, but I mean, the thing is, if it contains the point and it's closed, then it's that, and you cannot decompose it further, right? C1 or C2, one of the two would have contained X. And so you might as well just take C1 or C2, okay? The question is, are these all of them? And in general, not. So whenever your topology is coarse enough, then you get more irreducible sets than just closures of points. All right, so here's an example. I guess the most simple, non-trivial example. Take the unit interval with the cofinite topology, which is what? It's the topology where the whole thing and the empty set are of course included, and also the open set are all those sets whose complement is finite, so the cofinite sets. You know, these are closed in their unions and finite intersections and so on. All right. Now, the whole set is closed, of course. It's irreducible because you cannot write it as a union of, say, 0 to a half and a half to 1, because those are not closed sets in your topology, right? However, this is not the closure of any point, right? Because the points are closed here. So the closure of any point is just the singleton of that point. So here we have a non-irreducible an irreducible closed set that it's not the closure of a point. One might say, okay, but this is just one of those counter examples in topology, right? Why would you want to put such a topology here? It's not natural. I want to argue that sometimes it is, okay? So things of this form are very natural to study in, for example, algebraic geometry. If we go on dimension 2, say for complex numbers, then you can put what's called the Zariski topology, okay, for which the closed sets are solutions to polynomial equations. And those tend to be lines that, unlike my picture, do not terminate, like they are either closed or infinite, all right? Now, those things are closed sets. And they're irreducible because For example, half of a line is not a solution to an equation in general. So those tend to be reducible, and these are not closures of points, right? Because closures of points, again, are points. So this situation is sometimes very natural, and you don't want to put a finer topology here, because then you don't have a lot of things that you usually have in algebraic geometry, like Munchtel-Ansatz and so on, right? So these irreducible closed sets are, in some sense, something you have to live with and try to study their properties and use them to your advantage, all right? Include them in your formalism. Right, so that's for topology. What about measure theory? What happens there? Okay, no, before. A topological space is called sober if every irreducible closed set is a closure of a unique point. So this is a two-part definition. First of all irreducible closed sets are closures of points, right? There's no exotic irreducible closed sets, but also of a unique point. So that's the situation that we looked at before, where the topology separates points, all right? The closure is injected. So space is sober if both of these conditions holds. Now, given a generic topological space, you can always soberify that, which is a monad gives you an idempotent monad, and it works in two steps. So first of all, you take what's called the Kolmogorov quotient or the T0 quotient, as in, remember this equivalence relation of points that the topology cannot tell apart? Well, you identify any points that you cannot tell apart, right? So you take equivalence classes of that. And then you add in all the irreducible closed sets. You can do it in a way that inserts them, so to say, correctly into the same topology. So in a way that's induced by the original topology, you can keep the same frame. And that then adds extra points to your space. Okay, the resulting space is sober. This is usually what you do in algebraic geometry. If instead of talking about maximal ideas, you take prime ideals, and you talk about the spectral topology sometimes instead of Zariski. Okay, so you throw in all these extra varieties as points, sometimes called generic points of your space. So this operation is a monad, and this map that I've depicted here is the unit of that monad, and it's an idempotent monad. So once you have a sober space, if you do this, you're back to where you were, because now the irreducible closed sets are just points. Okay. All right. In measure theory, again, you can obtain measures from simpler measures, this time by summing them or by taking convex combination. All right, you just sum the two measures, you have again a measure. This is a little bit like before when you were taking unions of closed sets. Now, if a measure cannot be obtained in this way, you call it irreducible. Now, keep in mind here, I'm not allowing negative measures and negative numbers, right? So everything is like a positive cone. So these things are something like the extreme points of your convex set or of your cone, okay? So imagine if you have the positive quadrant, then the vectors on the axis of the quadrant, you cannot obtain them as linear combination. The rest of the quadrant, you can. So it's kind of the same thing here. So you say that a measure is irreducible if, whenever you express it as a sum of two measures, then these two measures are, well, you cannot say they are mu, but they're scalar multiples of mu. All right? Because of course you could rescale and sum twice the same thing. For example, you could have 1/2 mu, right? So we're saying that that's the only possibility, all right? So the mass is all in the same place in some sense. So these are basic building blocks for measures. Now you can see this, these are a little bit like closed sets, but now it's quantitative, right? Now numbers are involved. There's all these real numbers, and it's kind of, before it was a yes or no thing, like a topology, qualitative thing, logic was involved. Here instead, it's how much, all right? So this is a lot more quantitative, but apart from that, it's very much analogous, all right? As you might expect, Dirac deltas are irreducible, and so are their scalar multiples, of course. Because you know, you've expressed the delta as a sum of things and the mass is just there again. It's like a shorter column maybe, but in the same place. And one may ask you, all right, are there non-trivial irreducible measures? Is it like for closed sets that is there exotic irreducible ones? The answer is yes. So first of all, remember when we formed this countable, there's a cofinite topology. Here we're doing kind of the same, but the sigma algebra version. Remember, what's finite for sigma algebra becomes countable. That's kind of the analogy. And so the analogous thing to the cofinite topology is the countable, co-countable sigma algebra on the unit interval. What is that? So measurable sets are the whole thing, the empty set, and then countable subsets and co-countable subsets. So they're complement. So all your measurable sets here, in some sense, are all, nothing, essentially all, and essentially nothing. Okay. Now, as measure, you take, well, I want to say the restriction of the Lebesgue measure to this sigma algebra. So basically, it gives measure 0 to all the countable sets and 1 to all the sets with a countable complement. So basically, it gives measure 0 to the stuff that's nothing or almost nothing, and gives measure 1 to the stuff that's everything or almost everything. All right. Now, this is irreducible because, again, you can not really say that this is half a measure on like half the interval and half the interval, because the sigma algebra cannot tell those things apart. You cannot split the unit interval into halves here. Also, this is not a delta, right? Because if it was a delta at some point x, now the singleton with that x is measurable, and it would have measure 1 if it was a delta. But no, all singletons have measure 0 because they're countable. Okay, so the measure is like spread, but it's irreducible. Okay. Now, just like for topology, when we say, okay, this looks like one of those very exotic counterexamples, why did you put such a coarser sigma algebra? Why didn't you throw in all the usual Borel or Lebesgue measurable sets here? Well, okay, sure, I didn't, but I want to argue that once again, these structures might come out naturally in some contexts. You remember before for the topology, those things come out naturally in algebraic geometry. And in measure theory, these things sometimes comes out naturally in ergodic theory and dynamical systems. So consider the circle and take an irrational angle rotation in your circle, like a fraction of the whole thing, which is an irrational fraction, right? So what I did here is I drew a random angle. This is irrational with probability 1, okay? Now, you know that these angles, if you keep rotating, they never get back to the same spot, right? They tend to, like, in some sense, fill up the whole space, but of course, just countably, all right? And I'll form what's called the invariant sigma algebra. So take a measurable set that's measurable to begin with, like a Lebesgue measurable set, or Borel. And suppose it's closed under rotations, as in the sense that if you rotate of this irrational angle the whole set, it remains itself. Okay, it's not mapped to itself, it really remains equal to itself. Now, those sets, the invariant measurable sets, form a sigma algebra. So you don't have to like generate a sigma algebra from them. They are a sigma algebra. You can see that if something is invariant, then its complement is invariant, the countable union of invariant sets is invariant, and so on. Okay, so that's a measurable set, measurable space. Now the volume measure, so again, restricting the Lebesgue measure of the circle to the sigma algebra, again, if you want the central volume of this thing, is again irreducible, but it's not a Dirac delta. Okay, so why is it irreducible? Well, once again, you cannot really say that it's the sum of, say, half the circle and the other half of the circle, right? Because the sigma algebra cannot tell apart, just like above, cannot tell apart the halves of circle, because if you take a measurable set that just covers half of a circle, then it's not invariant, because if you rotate it, it's not, it doesn't remain itself, right? So it's So you can't split this measure into simpler ones. At the same time, this is not a Dirac delta either, because so suppose you take a point at which the thing should be a Dirac delta, all right? And now rotate this point forward and backward and keep doing that, all right? And imagine infinitely many times, forward and backward. Now you get a countable set that is dense in the whole space. And the resulting set is invariant, right? Because if you rotate it, then it stays on itself. So that's the set of your sigma algebra. Okay. But now, if the measure were a delta at one of these points, then this countable set would have measure 1 because it contains that point. However, this is a countable set, and so it has measure 0 because it's almost nothing. It's dense, but it's not, it's not massive. Okay. And so this set has measure 0, and this is true no matter which point you start from. So your measure is not a Dirac delta. Okay. So again, it's an exotic, irreducible measure, right? And I want to argue this is not a very exotic, undesirable thing, but it's a feature. So here here is an equivalent characterization of these objects. Let's normalize all your measures so that we don't have to deal with rescalings and things are a little bit simpler. And now for a probability measure, then the probability measure is irreducible, first of all, if and only if on all your measurable sets, it gives either measure 0 or 1, nothing in between. Nothing can have measure 1/2 and so on, right? Now, ergodic measures are defined. So the modern definition of ergodic measure is exactly those measures that are 0 or 1 on the sigma algebra of invariant measurable sets. Okay. So ergodic measures are irreducible by definition. That's exactly what they are, right? So it's not like ergodic measures sometimes are irreducible and that's undesirable. No, that's exactly what they are, right? It's not even a natural thing in ergodic theory. It is that thing. It's the whole point, all right? But there's more equivalent conditions. So another one is that for each pair of measurable subsets, then the measure of the intersection is the product of the two measures. So if you know probability theory, this precisely says that A and B are independent. So equivalently, a measure is irreducible if and only if it makes each pair of events independent. So you know that deterministic measures like deltas have this property, right? The deterministic measures are independent of itself. And in probability theory, there are these theorems called 0-1 laws. So a random variable satisfies a 0-1 law if all the events are probability either 0 or 1. And equivalently, that's characterized as those things which are for which each event is independent of itself, or equivalently, any two events are independent. So those measures, these laws of 0-1 random variables, are exactly the irreducible measures. In terms of measurable functions instead of measurable sets, supposing all the integrals that you need exists, then equivalently the measure is irreducible if the integral of the product is the product of the integrals, all right? So if you want, it's something like the integration functional defined by the function is a ring homomorphism. So if you remember, closed sets are irreducible if equivalently they're something like completely prime filters and so on. So it preserves some algebraic structure. This is the equivalent for measures. They preserve products. It's products or intersections are a little bit like meets. And so this is kind of like this completely prime filter condition, but for measures. So you see, once again, they're kind of like closed sets, except that it's quantitative. Numbers are involved. All right. But so you see, all these things are like very natural properties, and these measures are in Nuisance. Sometimes these are exactly what you want. They come up naturally in probability as laws of 0-1 random variables and in ergodic theory. Okay. Now, all right. So these are natural things. We have to deal with them. We cannot avoid them. But can we sobrify measurable spaces in a similar way to topological spaces. So since we have to deal with these things, is there a monad that can allow us to deal with these things and add these as points? Okay, so let's start with a little bit of category theory. So this is not the first time sobriety comes in this context. Similar ideas were had by Paul Taylor in his papers, but here it's a little bit of a different situation from that. Consider a monad on a category with a unit eta, all right? Now, this diagram is a fork. What do I mean by this? It's not commutative because the two blue arrows are not equal in general, but it's a fork in the sense that the composites are equal. So eta eta is the same thing as the eta eta, right? Above and below are equal. Why? Well, you can rewrite this as a naturality diagram for the unit of your monad. Okay, so this is a fork, and one might ask, is this an equalizer? Well, you say that the monad satisfying this equalizing requirement, as called by Maggi, but the concept is probably older. So the equalizing requirement holds if this thing is an equalizer at each object. All right. For example, look at the power set monad on sets. So it takes a set and gives it subsets. The unit of the monad is forming singletons, right? So you see now, if you take an element of Tx, so a subset of X, then you can either form the set containing only that set. So it's like a singleton of sets. Or you can apply T eta, which is like apply eta term-wise, element-wise in A. So for each element of A, form the singleton. So above we have a singleton of sets, and below we have a set of singletons. These things are equal if we have a singleton of singletons. So basically if A has only one element. All right. That's the same thing as saying that our large A comes from the unit of the monad. So that's precisely saying that the equalizer condition holds. Okay, so the power set satisfies the equalizing condition. This is related to the fact that sets are somehow powdery or granular, so the points can be exactly split apart. There's something about separating points and also about like that's all that there is to it, right? So as you might expect, this is not going to hold in categories that have some extra cohesive structure of some kind. So let's look at topological spaces and form what computer scientists call the generalized Hoare power domain, Tony Hoare, and what mathematicians call the lower Vietoris monad on topological spaces. So it's a little bit like a power set monad, but a topological version. You take a topological space and take the set of its closed subsets. All right. Now the unit is not just singleton; it forms closures of singletons. All right. So you can see this is already going in a direction that we want. Right now, we have to put a topology in the space of closed subsets, and we call we put what's called the either lower topology, lower Vietoris topology, or the hit topology, which is the following. What are the neighborhoods? The neighborhoods are generated by this hit of U. So take an open subset of X and look at whether closed sets hit it, meaning if they intersect it non-trivially. All right. So a neighborhood of this closed set C is all the other closed sets that intersect this set U non-trivially. All right. It's like something like if they touch, if they overlap. All right. All right. Proposition. The equalizer of this pair is exactly, it's not quite X in general, but it's a set of irreducible closed subsets. All right. So HX is all closed subsets. SX is the subset of that of irreducible closed ones. You can prove that a set is irreducible if and only if it is has the same result across these two maps. So the equalizer of this is exactly the sobrification monad. Now, We had other ways of obtaining the sobrification monads. This might be not shocking. The question is, can we do this in other situations? We can. So let's look now at the Giry monad or probability monad on MES, on the category of measurable spaces. So it takes a measurable set, a measurable space, and it gives the set of probability measures on it. The unit is Dirac deltas. So it takes a point and gives a Dirac delta measure over it, measure defined by that point, naturally. Again, Px, so far as just a set, we have to put a sigma algebra on it. And we put what's called the Giry sigma algebra, which I want to say is kind of like the hit or topology, but now it's quantitative. So instead of saying whether they overlap or touch, here it's like, how much do they overlap? How much do they hit each other? So instead of just taking a measurable, like an open set or a measurable set, you take a measurable set A and the number R, and now you're not quite neighborhoods, but like measurable sets are like generated by those that have measures mu, which give to A measure at least R, so that overlap have mass in A at least of that number. And you do this for all measurable sets and for all numbers. All right, positive, of course. So you see, this is a quantitative version of the lower Vietoris topology. Once again, measures are a bit like closed sets, but quantitative. All right. And now, the equalizer of this parallel pair is exactly the set of irreducible measures. All right. So dx here is not the distribution monad. P is the probability monad. Dx is the set of irreducible measures. So it's again the equalizer. So we have a way of obtaining it, which is just the same as for topological spaces, a formal way. Now, does this give a monad? It does. So first of all, without any assumption, besides having a category, a monad in it, and that the equalizers exist at each object, if they exist, then they assemble to a monad. All right? They assemble to a monad, which is a submonad of T. And you see here, by the universal property of the equalizer, first of all, dx is a subset of tx, a subobject of tx, because it's an equalizer, right? It's a regular subobject. So theta is regular monic. So for example, it's in measurable spaces, it's injective and measurable. And even more, it's a subspace embedding. Same for topological spaces. And this theta is a morphism of monads, you can prove. And the unit of the monad D is just this map here, classified by the equalizer. So you know that unit of T here makes a fork, so makes a, I want to say it makes the diagram commute, but it doesn't, but the composites are equal. And so it factors through the equalizer, and this orange map is exactly the unit of the new monad D, all right? So this is just proven by diagram chasing, but there's a little bit more. So if and only if this map here is monic, then the monad D is idempotent. Now, what map? So I said that theta is a very nice monic map because it's an equalizer. So it's regular monic. Under some very natural conditions, T applied to theta is again monic. All right. So not always, but very often. So this is, for example, the case for a Hoare power domain and for a Giry monad. That's sufficient and necessary for having the monad D idempotent. So it really behaves like a sobrification monad. It makes something kind of sober, and then it's sober, and that's it. You don't go any further. All right. In particular, this tells us that the monad, the submonad of irreducible measures, is idempotent. Okay. So, definition: X is sober if and only if one of these two conditions holds. These two conditions are equivalent. Either Maggi's equalizing requirement holds at each object X, at the object X, or if the monad of the unit of the new monad, so this map eta D, is an isomorphism. So these two conditions are equivalent. You can see by looking at the universal property of this equalizer diagram above. All right. So when any of these two conditions holds, you call X a sober object. Now let's see a couple of examples. So first of all, we saw that the power set monad satisfies the equalizing requirements. So every set is sober. Okay. This is true for most other monads on set. Of course, not every monad on set has an injective unit. So you can take the terminal monad, which maps everything to 1. That would not satisfy the equalizing requirement, of course, right? But most interesting monads on set have this property too. All right. Now, for the H monad, so there's a Hoare power domain, every object has as equalizer the set of irreducible closed sets. All right. So an object is sober exactly if it's a sober topological space in the traditional sense. So this recovers the usual notion of sobriety. For measurable spaces, and the Giry monad, then all discrete spaces are sober because you can just tell the points apart and there's no surprises. And the real line is sober, and so are all its powers, the unit interval, and so on, which means that all standard Borel spaces are sober. So these are usually the sets, the spaces where you want to do probability theory because these are very nicely behaved. And so unsurprisingly, all standard Borel spaces are sober. And you might imagine that standard Borel spaces, Hausdorff spaces, if you put the Borel sigma algebra in it, are sober too, because you can tell points apart. And we can say even more, actually. We can say that sober topological spaces, in the traditional sense or in this sense, if you put on them the Borel sigma algebra, then they are sober also as measurable spaces, also in the sense of the Giry monad. So equivalently, this functor, I don't know what's happened to this diagram here on the right. There should be top, the category top, and there's a functor from top to mes, which takes the topological space and puts the Borel sigma algebra on it. This functor preserves sobriety. Now be careful, the two notions of sober are different left and right, but they are compatible, okay? So there's no loss of ambiguity here. No loss of generality. Calling a sober, say, topological space with a Borel sigma algebra is compatible. Like if it's sober for, if it's sober as a topological space, then it's sober for the Borel sigma algebra. Okay. All right. So I'm going towards the end. Why is this a form of point-free measure theory? There's a lot of researchers that study, for example, abstract sigma algebra, so sigma algebras which are not sigma algebras of subsets, but they're more like Boolean lattices with like countable joins and so on. A little bit like frames as opposed, like in locales, as opposed to topological spaces, right? And so what happens in topology? Well, in topology, a point of X is a map from 1 to X, like from the 1-point space to X. So in terms of frames, it should be a map from the topology of X to the topology of 1. So here we want a map from the sigma algebra of X to the sigma algebra of 1, which is up to isomorphism, the 2-point lattice, right? So now, a morphism of sigma algebras here. So sigma algebras have the empty set, have complements and countable unions. So a morphism of sigma algebras would have to preserve all those. And well, countable unions are just the maximum in 0, 1. But you see, this is exactly what irreducible probability measures are. Now, of course, measures in general don't just take values in 0 and 1, but also on the stuff in between. But if they're irreducible, then they don't go in between. They're just 0s or 1. So they're just the same thing as these objects. So if you want irreducible measures, basically the points of a sigma algebra in a way that's very analogous to points of a locale. Now, again, there are people that study these abstract sigma algebras and measure algebras. I don't know if they have looked at the notion of what's a point of a sigma algebra, like for locales, but I suppose if they have, it has to be something like this, right? At least if you want it to be analogous to the point-free topology case. But either case, I want to argue this is a very natural notion, okay? So in some sense, irreducible measures are points that kind of should be there in a certain sense. And they are there when you sobrify your measurable set, okay? Last two things. First of all, there is a link to theoretical computer science, namely the notion of Tankability, all right? So take a monad on a category and look at the Kleisli category. A Kleisli morphism is called Tankable. I should say Tankable for the canonical, Tank for structure on the Kleisli category. If this diagram on the right commutes, where now, be careful, the unit of the monad is a morphism in the base category, but that defines also a morphism in the Kleisli category through the adjunction, or if you want, by just adding the unit of the monad again, like eta eta, so to say, all right? And now you see that this diagram here would commute if F was pure. Like in the base category, this diagram commutes by naturality of eta, okay? But if F is a Kleisli morphism, there's no guarantee this will commute. And if you want, this is kind of measuring how far we are from being pure. Really, this measures how far we are from being Tankable. So a Tankable morphism is a morphism that makes this diagram commute. All right. So a Tankable is something like freezing something. Okay. So imagine that F is rolling a die or recording some audio from some input that's not predictable. Then you see that these things are not the same. So one thing is, for example, creating a program that always records the same audio. And another thing is recording an audio and then memorizing it. So if there's some randomness or some effects involved, this diagram tends not to commute, okay? So for more on this, I refer you to this reference of Furman, and there's a lot more literature on Tankability, okay? But it's something like effective programming tends not to be Tankable. Now, this morphism in the Kleisli category is Tankable if and only if. When you write it down as a morphism of a base category, then it makes a fork here. So again, the composites are equal. But then you see by the universal property of the equalizer of these two maps, if there is an equalizer, that's exactly saying that it factors through D to the irreducible things. So now, suppose there's a monad D of T exists, like all the equalizers exist. You see that since we have a submonad of T, then you have a subcategory of the Kleisli category, right? The Kleisli morphisms of D are a subset of the Kleisli morphisms of T. Which subset? Exactly the Tankable ones, all right? So the monad D is exactly the submonad of T that classifies the Tankable Kleisli morphisms. So it has an interpretation in terms of computer science. So what are Kleisli morphisms? Kleisli morphisms have an effect, and this effect is not so strong if they are at least Tankable, right? And this is kind of the idea here. So for non-determinism, it might give you a closed set, but it's not that wide, right? Because it's an irreducible one. So it's somehow one of the small ones, so to say. Just as well, it might have probability involved, but it doesn't give you a generic probability distribution, but it's an irreducible one. So one that is 0, 1, that is certain about which events happen almost surely. Like each event is probability 0 or 1. So it's not that probabilistic, okay? So Tankable morphisms are classified by the monad D. Moreover, another situation where this comes is Markov categories. And if you know, my research involves mostly Markov categories. So this is how I came across all of this, because it has relations to Markov categories. So in a Markov category, Take, for example, a commutative affine monad on a Cartesian monadal category, right? So affine so that every morphism is normalized or discardable. Then a Kleisli morphism is called deterministic or copyable if this diagram on the right commutes, which is a little bit like Tankable, but now it's different. So if it commutes with copying, all right? So what does this mean? Well, I like saying randomness is doing the same thing twice and expecting different results, right? So one thing, if F has a randomness, then applying F and copying the result is the same, is not the same thing as copying the input and applying F twice, because in these two instances, you might get different stuff, right? On one side, you have correlation, like the two things you get are gonna be equal with probability 1. On this other side, they are independent given the inputs, they're gonna be different, okay? In general. So if this diagram commutes, you call F deterministic. And again, if F is pure, like if F comes from the base category, then this diagram just commutes by naturality of the copy on the Cartesian structure. But here in the Kleisli category, we don't have a Cartesian structure in general. So this does not commute, right? Not in general. Now, a monad is called observational. We call it like this. We came up with this name. Actually, Sean Moss came up with this name. If for every object X, here I want to say you can tell apart elements of TX by taking IID samples, like independent and identically distributed, by just repeatedly sampling independently, by doing experiments many times, a bit like you do in science, right? So let's try to do so for this. So you take TX, which if you want is like your measure, it contains your probability measures, and you copy them n times, n is finite but arbitrarily large, and then you sample them. So what this map epsilon is the co-unit of the monad on the Kleisli category, so of the co-monad, I guess. So on the other side of the adjunction. So what does that do? It takes a probability measure and returns a random element sampled according to that distribution. So with that law. In probabilistic programming, this is exactly the sample command. Or in, say, in basic probability, this is the, when you take Bernoulli of P, right? And then you get either 0 or 1 according to P. So it gives you a kernel, which is like a random element distributed according to your distribution, all right? So you do this for each copy of n, for each copy, for each n, all right? So what you're doing here, you are saying that these maps here need to be jointly monic, a jointly monic family for all n in the Kleisli category. So what does that mean? That if two maps into Tx, for example, two elements of Tx, if we are in a concrete category, can be told apart if you take a large enough n and like arbitrarily large and sample repeatedly like n times from those probability measures. So you can test the quality of probability measures by just repeatedly sampling, which is what people do in statistics, big data, or in any scientific discipline. You just repeat your experiment and see if the things are the same or not, right? So, so this is the case for the Giry monad, and is also the case for the Hoare power domain. All right. This also comes in the definite theorem, right? Because the definite theorem kind of says that exchangeable sequences are the same as probability measures, kind of, and so in particular, they can tell them apart. All right, so why am I saying this? Why are we talking about observational monad? Well, because in general, all the Kleisli morphisms of D, so the Tankable ones, are always deterministic, okay, are copyable. That's always the case. But if the monad is observational, then the converse is true. And so in particular, the morphisms of D, so the morphisms of D are exactly the deterministic morphisms, all right? Now, this theorem looks a little bit innocent, but remember that we had all these equivalent characterizations of irreducible measures that involve like independent events and all that. So that's exactly this theorem for the Giry monad. So this theorem is an abstraction of these equivalent characterizations of irreducible measures. And it's also an abstraction of these equivalent characterizations of irreducible closed sets. You know, they could be sets that are non-trivial unions. They could be sets that make completely prime filters. They are frame homomorphisms into the trivial one, and so on. So all these are equivalent. And again, that's an instance of exactly this theorem, that you can view these things as equivalently deterministic morphisms or states, or tankable ones, and those things are exactly the same for these monads. All right. So this kind of unifies also all these equivalent characterizations. This is why they happened. And again, of course, this is relevant for Markov categories, because you want to quantify sometimes how much deterministic morphism fails to be, for example, a measurable function. And this is exactly how it does. So through this submonad D. Okay, so I will stop here. Here are some references. And there's more material coming. Also, for the stuff that I have mentioned in this talk that is not listed here, please look at the references inside these references, okay? Especially the references here of the first paper for all the theoretical computer science content, okay? So thank you for watching. This is not live, so I cannot really take questions, but if anything is not clear, feel free to contact me in any other way. So if you saw this video, you probably know how to find a way to reach me. All right. Thank you for watching, and bye.